and I'm back to review Unit 6 of AP Physics 1, Simple Harmonic Motion. Okay, so first thing, this is a kind of a chunky phrase, simple harmonic motion. Really what it is it's just kind of almost just an infinite cycle in a perfect world where there's no like air resistance or frictional yada yada yada. It's just a perfect just a cycle of something going back and forth, and it's that there's a restoring force that pushes something back to its equilibrium and then past its equilibrium, and then the restoring force pushes it back to the equilibrium on the other side, and then it just keeps going. Think of a pendulum. In fact, that's one of the examples. So, yeah. And so this is kind of a typical graph of what you'll see a lot of for simple harmonic motion. It's just like a sine curve, just something going. Oh, there's a the line's equilibrium, and it just goes past, and then there's a restoring force trying to take it back to the line here, so it goes down, and then now there's a restoring force trying to take it back to the line here, so on and so forth, forever. And then the space between cycles is called a period, which we will get to here. So, two types of simple harmonic motion. Pendulums right here, where it's just swinging back and forth, and then springs, where sometimes you can have two springs, like one over here and one over here, and then the object will just slide back and forth. You can have a spring hanging from the wall so that there's a force downwards from gravity and a force upwards from the spring. You can have a spring over here, just one spring where it slides back and forth because it overextends and then underextends, yada yada yada. So, period is equal to 1 over frequency. So whatever the frequency is, like however many times this happens, I don't know, per second, that's how long the period is. 1 over that. And then, so period of a pendulum, the equations are slightly different. It's 2 pi times square root of the length of the string over gravity. And then this period of a spring is 2 pi times square root of mass over the spring constant. And then Hooke's law is force of the spring equals negative spring constant times displacement. Spring constant is going to be like 100 newtons per meter displacement. That's what a spring constant will look like. Okay, energy and motion in simple harmonic motion. So, didn't realize how redundant that sounds, but so a big thing is that when you're at equilibrium, there is no potential energy because there is no force acting on you. There's no acceleration at equilibrium. You're at your highest velocity, which is why you still move, but there's only kinetic energy. There's only velocity. There's no force acting on you. There's no potential energy at equilibrium. But when you're at the edges of like the pendulum or the spring, that's where when you change direction, you have no velocity, but there's a massive force acting on you that's pushing you towards equilibrium. And because there's a big force, there's a lot of potential energy, whether it be spring potential or gravitational potential, etc. Okay, so the example problem 1. Which pendulum will have a longer period? Pendulum A, the mass is 10 kilograms, length is 2 meters. Pendulum B, mass is 4 kilograms, length is 3 meters. So the mass here is a distractor. This is completely irrelevant. It's not in the pendulum equation. So you can see, though, is that the only thing that you sub in is the length. And since it's in not the denominator, the opposite of the denominator, which that word is leaving me for the second, but it's the top of the fraction, which means it's really just the bigger number means the bigger period. So B will have the bigger period because it has the larger length. Okay, example problem 2. A mass of 0.25 kilograms is fixed to a 0.5 kilogram spring. When the system is stretched 1 centimeter from equilibrium, it takes 3 newtons of force to hold the mass in place. If the spring is stretched by 4 centimeters, what's the restoring force? So you use Hooke's law. Since before it was 3 newtons to hold it in place, which means negative 3 newtons pulled, the new force is 4 times that. So it'll be negative 12 newtons instead. So, hope that makes sense. Thank you.